Hi all, we got another adder video here. The last time we talked about the 4-bit CLA adder that I had designed, and I mentioned that there were some issues that I wanted to fix and some things that I wanted to try and optimize. I was able to figure out how to do a couple of those things, but most importantly, I was able to expand it to 8 bits wide. So this is a 4-bit CLA adder, and this is an 8-bit one. And interestingly enough, it's still able to fit within 8 tiles across, so it's still one wide tileable. However, you will notice that the machine is much wider in length. This was just some development stuff that we were doing. You can ignore that for now, but basically this is the main machine. So as you can see, it's a lot longer, but that does correspond to needing more bits. There's essentially more logic that needs to be done to actually generate and propagate the carries. But it still works just fine. So let's do a carry test here. We've got 127 plus 1. Notice that I also made it so that the 0th bit is properly on the right now. I don't know why I built that one mirrored, but I did, but I fixed it. So we'll go ahead and send that off, get a little bit of a lag spike, and you'll see that at the very end here we get our 128 out from the sum. I also put a little bit of a carry out or overflow indicator here, just in case. Interestingly enough, one of the other things that I was able to fix, I don't know why I didn't see this the first time, but this is a very inefficient way to shift signals across. When you have access to 2 rail types, you can just do something like this, and it works much, much better. It's much more compact to do that. So saved a couple of delays on the output side here, but pretty much everything is still the same. It works the same way. I was able to do the input busing a little bit better as well. So instead of having to place blocks to extend for observers, I was able to compact it down to just these 2 things. Oh, that was the wrong side. We did it on this one. There we go. But yeah, 8-bit CLA version is working just fine. We could do, I don't know, another arbitrary calculation here. Maybe just a alternative bit one, just to show that there's no speed difference between carrying and not carrying. You run down, and we got all the bits showing up. So, but yeah, just wanted to give a quick update on that and show that not only is 4 bits possible, but 8 bits is also possible. Now, if you wanted to do more than 8 bits, you can continue to do so. As you can see, I've got the individual AND gates sort of separated onto these different rail platters. The reason why is that for the inputs to the AND gates that are necessary to do the carry math, you essentially, what you need is the number of AND gates is going to be 1 more than the number of bits summed all the way down to 2. Now that's a little bit complicated. I'll explain what I mean. So this is a 4-bit machine, and the number of gates that we require horizontally, or gate inputs, is 5 plus 4 plus 3 plus 2. So that is 1 more than the number of bits. So we start at 5 instead of 4, and we sum all the way down to 2. And that's going to be the number of inputs that are required to actually make that logic work, as well as you can think about it, the number of horizontal tiles that we're going to need to actually fit that design. So if you do that with 8 bits, you start at 9 and you sum all the way down to 2, you get 44, which is very convenient because that's 1 less than 45. And 45 is divisible by 9, which is the maximum distance that a signal can travel over a set of rails. So you can see that I've got 5 sections here, and I use that extra one that's not being used as the input for the OR gates. So essentially you've got the AND gates up here and then the OR gates down here. But it still works. I'm happy with how it works. And that's what I've got to show you. So thanks very much.